Welcome everybody to our fourth live lecture. In today's live lecture, we're actually going to cover sections in your text that are called Just in Time 21 through 27 about rational and radical expressions and rational exponents. This lecture does assume a strong understanding of factoring polynomials. So if you do need a review in that, you can also find that information in the Just in Time section. And if you need more than what's provided in your text, I can also direct you to additional resources. But again, this class does assume that you already have the basic skill of factoring polynomials, and we'll be using that today when working with rational expressions. So rational expressions, basically you can see that word ratio right there, is just a quotient of two polynomials. So it's basically a fraction, but typically we have variables in the numerator and denominator. The most basic rational expression is just a plain fraction, so you can see those two. But typically when we're looking at an algebra class, you're going to see something a little bit more complicated like you do here, where you have a fraction, but again, you have polynomials in the numerator and denominator. The domain of a expression like this, like all the ones we've seen, is defined for all numbers where you can actually get a valid answer, right? So the one thing we have to watch out for here is division by zero. So our domain is going to be all numbers except those that make the denominator zero. So that's the issue we have to watch out for here. We don't have to watch out for imaginary numbers, just the dividing by zero. So for my first example, and I'm just going to rewrite it because the printing is a little small, my expression is x squared minus 4 all over x squared minus 4x minus 5. So we're just asked to find the domain here, and you need to make sure the denominator is not equal to 0. So I set my denominator here, basically equal to 0, right? We're going to just solve, and I'm going to find the two values that I'm going to exclude. We're going to see more than one answer here. When you actually start having higher powers, you can have more answers. So when you have a square, you can have up to 2 different answers. If I had a cube, I would have up to 3 different answers. So that expands. Now there's different ways to factor polynomials. I'm not going to go through all the different techniques. One way you can do it is trial and error though. So you can think about, your first piece here and what factors would give you x squared, maybe x times x. And then you could think about your last piece and think about, well, which factors would give us a negative 5? And it's either negative 1 times 5 or 1 times negative 5. And then what you do is you set it up and you try different combinations here such that when you multiply this out, you get the original problem. So I'm just going to go up here and show you how this checks out. And again, I'm not going to do this every time because this is something you should know. But if you multiply this back out, and you combine your like terms, you should get the original polynomial, which we do. So that's how you know if you factored correctly. Once you've factored, you can solve this by setting each factor equal to 0. So I would set x minus 5 equal to 0, and then x plus 1 equal to 0. And then I go ahead and I solve. So I add 5 to both sides, I subtract 1 to both sides, and I have my two answers of 5 and negative 1. Now let's think back to the question we were trying to answer here. So our question was about finding the domain. So these are the two values that would make the denominator 0. So in this particular case, even though they give us the answer, we actually don't want these values, right? They would make the denominator 0 here. So our domain would be all x values as long as x is not equal to 5 or negative 1. So that's one way we could write it. So all values, but x is not 5 or negative 1. Or we can write it in interval notation. So going from negative infinity to negative 1 to 5, and then 5 to infinity. So using those parentheses in that u, we're skipping over the negative 1 and the 5. Let's do one more here. And again, this is a great time if you want to try it, you can. So I'm going to look at my denominator. I want to find the domain. So I need to make sure my denominator is not 0. So I have 12x squared minus 12 equals 0. Now I actually can factor a 12 out here, and I get x squared minus 1 equals 0. And then this factors as well. So this right here factors into x plus 1, x minus 1. So this is the difference of two squares. And again, if you haven't seen that technique in a while, it's definitely one to look up. You have a square minus a square, and it always factors into this plus or minus format. So that's how this one can factor. And then if I set my pieces equal to 0, well, 12 equals 0 doesn't really matter, right? So I don't have to worry about that one. But then I have two others I can solve. Here I subtract 1, here I add 1. So I have x equals -1 and x equals +1. Now remember, these are values that we don't want, right? So our domain here are x values, but x cannot be -1 or 1. In interval notation, we're going from -infinity to -1, -1 to 1, and then 1 to infinity. Now there are other ways to solve this. Another way you could have solved this is you could have added 12 to both sides, and then you would have had 12x squared equals 12. You could have divided both sides by 12, x squared equals 1, and then you could have taken the square root of both sides as well. Just don't forget that we take plus or minus the square root. So you do get that plus or minus 1 there as well. So again, there's just different ways that you can do it, and you're welcome to use whatever strategy works best for you. Now, the other thing we do want to do is we want to simplify. So think about how we simplify fractions, right? For instance, if I had, 2/4, well, 2 is 1 times 2, and 4 is 2 times 2. So what we do is we cancel out the factor in common. Now, usually we think about this as like dividing by 2, right? You can do it that way. But you're basically canceling that factor of 2, and you're left with 1/2. We're going to use that same technique here, but with polynomials. So if you're trying to simplify, you do want to start by factoring. And you're going to factor both the numerator and denominator. So I've already factored the denominator. I've done all that work already. But for the numerator here, I do see that there's a 3 in common to all pieces, so I can factor that out first. And then again, I would keep factoring this piece here, breaking down the first part and the last part to find that combination that works, and 3x minus 1 and x plus 1 other combinations that work there. So what happens is that your numerator has become this. Your denominator became this when we factored. And then what you can do is, again, cancel the factors in common. And we cancel by groups here. So you can cancel the whole x plus 1 from the top and the bottom. I can't cancel anything here. I know you see a -1 in both, but you can't cancel that. You have to cancel it as a group because it is one factor. I can simplify the 3/12 though, right? I can divide those both by 3, and that becomes 1/4. So in the numerator, I have a 1 left and 3x minus 1. Well, 1 times anything isn't going to change that, so I'm just going to use 3x minus 1. And in the denominator, I have a 4 and an x minus 1. Now, a lot of times for rational expressions like this, they will let you leave your answer in what's called factored form. So you don't have to multiply it back out. So just make sure you read through your homework questions if they do want you to completely simplify and keep multiplying, or most times they'll let you leave the answer in factored form. And that's pretty common with rationals. We usually make that exception. Another thing I want to note here is that even though the x plus 1 cancels, it still is an issue in the domain. When we find domain, you do it before you simplify anything or before you perform any operations. So domain comes first, and then do whatever else you need to do. And that's really important. A lot of times, if you simplify early, you'll miss the fact that x plus 1 is an issue. So domain always goes first. All right, so let's look at some other operations here. Next, we'll do multiplication and division. So to multiply rational expressions, we multiply the numerators and denominators. It does help to simplify before we do this. And again, you're going to see a repeat strategy where we basically we factor everything first most times, and then that will allow us to cancel out factors in common, and it just makes the rest of the work much easier. So think about how we do like a regular problem, right? If you were multiplying a fraction like 1/2 times 3/4, we would see if there's anything that we could cross cancel first. If there's anything in common, there's not here, and then we just multiply straight across. And we're going to use that same kind of strategy. Look and see if there's anything we can cross cancel, and then just multiply whatever is left over. Now, we do need to factor. So that's not as easy as just 1/2 and 3/4. So the a squared minus 4 is going to factor into a plus 2, a minus 2. That's a difference of 2 squares. Oops, 20. And then everything else is pretty much already pre-factored. I can't do anything with a plus 2 or 16a. I do have a square here, but there's no plus or minus. I can't like break it down any further. So this is the only piece I need to factor. And then you're just going to look on top and bottom and see what is in common that you can cancel out. It's always 1 on the top for 1 on the bottom. So here I have an a plus 2, and here's an a plus 2 that can cancel. I don't have any a minus 2, so that will stay. I do see a 16 and a 20. Those both have a factor of 4, right? So I can divide the 20 by 4, and I get 5. And I can divide the 16 by 4, and I get 4. And I do see an a and an a squared. So those each have 1a. I can take away 1a from both. And then I rewrite what's left over. So in the top, I have a 5. I have 1a. And then I have an a minus 2. And in the bottom, I have a 4 left. I do encourage you to give a quick check and make sure you didn't miss any factors there. Before you complete your answer, but I don't see anything else in common. So this is the whole piece. Right. Now for division, we divide just like we do with fractions. So remember, for dividing fractions, if you have something like 1/2 divided by 3/4, what we did is we leave the 1/2 the same. We change the problem to multiplication, and then we flip the second fraction, right? We take the reciprocal or flip the second fraction. That's how we divide fractions. We're going to use the same strategy here. These are really just kind of messy fractions. And just like before with multiplying, if you do see something in common on top or bottom, you can cancel it. 4 and 2 can both be divided by 2. So I can do that division first, and then I multiply what's left. 1 times 2 is 2. 1 times 3 is 3. So I'm going to use a similar strategy here. So I'm going to leave my first part the same. I'm going to change to multiplication, and then I'm going to flip the second part. Okay, so that second part is the one that's going to get flipped here. Now, just like with multiplication, I'm going to factor everything because I want to try to cancel things. So what I have, the first group I can't do anything with. There's nothing to factor out there. For the second group, though, I do have some work. So I do see that they both have in common a 3 and an x squared. So I have a common factor I can take out here. I'm left with x plus 5. And then in the denominator, I have, let's see, x squared minus 4x plus 4. So that is actually going to factor into x minus 2, x minus 2. And again, the goal this week is to show you how to work with rationals, but it's assumed that you know how to factor. So I'm going through the factoring very quickly. If that's not the case and you need some review there are some sections in your text before these ones. Or again, you can send me a message and I can direct you to some videos that you can watch on YouTube as well, or you can just try searching on your own. Now that everything is factored, we're going to go ahead and cancel what's in common. So I have an x minus 2 and an x minus 2. I can't cancel these. Again, they're different. I know they both have x's, but they have to be perfectly the same groups to cancel. And then I do see a 3 and a 12. I can divide those both by 3. So that would be a factor of 1 left and 12 divided by 3 is 4. All right, so what do I have left in the top? I have a 1 and an x squared. I don't really need the 1 because 1 times x squared is just x squared. And then I have an x plus 5. In the denominator, I have a 4 and an x minus 2. And again, I would just double check, make sure there's nothing else in common that you can factor out. And when you're done, then we're all set. That's all we're going to do. And again, we're leaving our answer here in factored form. If you need to multiply it out, you could do that and distribute. But again, most cases, I would say like 9 out of 10 times, we usually leave the answer in factored form. Next, we're going to look at adding and subtracting. So think back to your regular fractions, right? If I had something like 1/2 plus 3/4, we can't add these. We would have to find common denominators. And we're going to do the same thing with our rationals. So for instance, in this case, I could use a denominator of 4. So I'd have to multiply the first fraction by 2/2 to get that common denominator. And then once I have it, I can just add 2 plus 3 is 5, and I keep the denominator the same. I'm going to apply the same strategy here. It's just that our LCD will be a little bit more complicated because we're going to have variables. So the first thing I'm going to do here is I am going to start by factoring. For adding and subtracting, you don't really need to factor the numerator. You can really just factor the denominators. So we're going to do that. So my first denominator is x squared minus 3x plus 1. And so we're going to factor denominators. And this one is going to factor. So 2x squared, it has to be x times 2x. And positive 1 is either 1 times 1 or negative 1 times negative 1. So you got to kind of play around with the combinations here and find the one that works. That's going to give you that minus 3 in the middle. And minus 1 is the one that's going to work there. For my other denominator, I can take out a 2, and I'm left with x minus 1. So how do you take these and find the LCD? There's different strategies to do this. The way I like to do it is I take my first denominator and I just bring the whole thing down. So I'm going to just rewrite the x minus 1 and the 2x minus 1. So I kind of just bring, the whole group down right away. And then what I do is I ask myself, okay, what is still missing in the LCD from this denominator? Okay, so if I look at this denominator, I have a 2 and I have an x minus 1. Well, the x minus 1 is already there, but the 2 is not. So I'm going to bring in the 2 because the 2 is the one that's missing. So basically, you're kind of combining both denominators together, but you don't need to have extra repeated factors. I don't really want 2 x minus 1s. If there's only one of them in each case, I just need 1. So I want to keep it as simple as I can. And this is going to be my common denominator. So what we're going to do now is we're going to just take our original problem. I'm going to take the x squared minus 4x plus 4. And then I'm going to write the denominator, but in the factored form. I'm going to leave some space. I'm going to do the same thing for the second one, but just writing the denominator in the factored form. And then I'm going to multiply by what's missing from the LCD. So if I look at the first one and I compare it to the LCD, the 2 is missing. So I'm going to multiply it by 2 on top and bottom. So you're going to multiply by what's missing to get your LCD. Same thing over here. I have the 2, I have the x minus 1, but I don't have this factor. So I'm going to multiply by that factor. Again, top and bottom to keep it balanced. Now, when you're multiplying on the top here, there really are hidden parentheses. So we're going to have to do distributing in both groups, okay? So here you're going to have to kind of FOIL that out. And let's see, what do I get? For the first group, we'll just come down here. I get 2x squared minus 8x plus 8. Then for the second group here, let's see, x times 2x is 2x squared. If I multiply by negative 1, I have negative x. 4 times 2x is 8x. And then 4 times negative 1 is negative 4. And I'm going to just put it all over the LCD. Now notice I just put the plus sign in the middle because that's what was here. I'm just taking a little bit slower. If it's a plus sign in the middle, there's really nothing left to do. We're just going to combine like terms. If you do have a subtraction sign, though, you would distribute that negative. So you just want to be a little careful. And I know it's going to look a little backward. I'm just going to put my answer up here. So let's see. I have 2x squared and 2x squared. So I have 4x squared. I have a negative 8x, a positive 8x, and a negative x. So that's going to be negative x. And then I have an 8 and a minus 4. So I have plus 4. And then my denominator is going to stay. Now I am done. You do want to always check though if you can simplify. So I will give that warning. If I try to factor 4x squared minus x plus 4, I don't get anything that's going to work there. And especially I don't get anything that works that's going to cancel with the denominator. So you would always check to see if you can factor the numerator further and see if there's anything that you can simplify and cancel. I'll tell you to save some time because these videos are already pretty long that nothing works. But you can try on home as well and make sure you're finding the same thing. All right, let's do a subtraction one. And again, I'm going to just start by factoring the denominators. So my first denominator is x squared plus 11x plus 30. Now x squared has to be x and x, but that 30 gets a little bit tricky, right? 30 could be 1 times 30, or it could be negative 1 times negative 30, right, using two negatives to make a positive. It could also be 2 times 15 or negative 2 times negative 15. 3 times 10 is also 30, as well as 5 and 6. So you do have quite a lot of combinations here to try. I'm not going to try all of them with you guys, but the one that's going to work to get the 11 in the middle is plus 5 and plus 6. If you multiply that out, you get that 11x. For the second one, again, the x squared is pretty nice. It's just x and x. But for the positive 20, it could be 1 and 20, or negative 1 and negative 20. It could be 2 times 10, right, or the negatives. And it could also be 4 times 5. And the one that is going to work there is going to be x plus 4, x plus 5. So for my LCD, again, I'm just going to combine everything together. I usually just take the whole first group. And then in the second group, I see what's missing. I'm missing the x plus 4, so I'm going to go ahead and incorporate that in. It actually doesn't matter the order that you write these factors in. I just like things in order, so I put the 4 first, but it really doesn't matter. Now, I do want to make a little note here, just kind of off to the side for a second. So notice how, because I have an x plus 5 already, I don't need to add a second one in. The only time you'd have to add a second one is if one of your polynomials has the same factor more than once. So for instance, let's say your first polynomial had the factors x plus 2, x plus 3, and then your second polynomial had the factor x plus 2, x plus 2. So in that case, your LCD would actually be x plus 2 squared, x plus 3. The x plus 3 comes from here, and then you do have an x plus 2, but because this one has 2 of them in the same polynomial, you do have to have 2 of them there. So this is the only time that you would repeat a factor in your LCD is if it is repeated in one of the polynomials as well. Otherwise, you don't need to have it written more than once. All right, so let's keep going. So my first part, I have x over x plus 5, x plus 6. And then, oops, sorry, this is a 5 over x plus 4, x plus 5. And then don't forget, you're going to multiply by what's missing. So here the x plus 4 is missing. Here the x plus 6 is missing. Be careful and make sure you distribute. X times x is x squared. X times 4 is 4x minus 5 times x is 5x, and 5 times 6 is 30. All right, so we're going to go ahead and subtract that through. This is where you have to be a little bit more careful. So I have x squared plus 4x minus 5x minus 30. all over that same LCD. And then combining like terms here, you get x squared minus x minus 30 over x plus 4, x plus 5, x plus 6. These can be a lot of writing sometimes. And you're basically done. However, you do need to check. So you do want to always see if you can simplify further. So you actually can break down this numerator, and it breaks into x minus 6, x plus 5. So you actually can factor this. So you do want to get in the habit of just checking to see if you can factor. A lot of them you can't, but there are always going to be some that do actually factor, like this one. And then if you can factor, you would see, can you cancel anything in common? Again, you can't always do that, but here you have that same factor of x plus 5. So I'm going to go ahead and cancel that out. I cannot cancel the 6's here. One has a minus, one has a plus. They're different, so you have to leave them. All right, one last thing that I do want to talk about on this page is just don't forget with the domain. When you're checking domains, if you have a problem where you have to actually provide that, then you would do it right at the beginning. So, if I look at my original domains here, I would have to exclude -5, -6, and -4. Even though the 5 gets canceled at the end, remember domain is always at the beginning. So you're looking at where your denominator cannot be 0 at the beginning of a problem, not at the end when finding domain. All right, so there's one more piece here I do want to show you guys about rationals. And these are called complex rational expressions. And they are complex because they're basically fractions in fractions. So before we get into this really hard one here, let me show you a little bit of a simpler one. So here's a simpler one where you have 1 over 2x and then in the denominator of x over 3y. For the simple ones, my favorite strategy is to just change this into a regular division problem, right? So see how you have that division line? That really is a division bar. So you have 1 over 2x divided by x over 3y. Now it's simpler because there's no plus or minus. See how these have plus or minus pluses here? They get a lot more complicated when you have addition or subtraction. If you don't have addition or subtraction, they're actually not that bad. I can change this to division. And then don't forget that you can switch to multiplication and then we flip that second fraction. Now, if there's anything that you can cancel out, you would. I can't cancel here though. So 1 times 3 is just 3. So I have 3y. And then x times x is x squared. So I would cancel, anything across that I can, or factor if it's more complicated and cancel. And then I just multiply what's left. So for your simpler ones, even though they're pretty scary in the beginning, they're really not that bad because you can just change this to a division bar. Now, these ones are a lot more complicated because you have addition and subtraction as well. So I'm going to show you 2 different strategies that you can use here, and it's your choice which one you want to use. It doesn't matter to me. So the first strategy is exactly what I just showed you guys, just changing this right here to division and rewriting it. So you'd have the numerator is 1 over a plus 1 over b, and then you're going to divide that by 1 over a cubed plus 1 over b cubed. Now, the problem, though, is that, think about order of operations. You have to do parentheses first. I can't just flip these guys individually. When I change to multiplication, I have to have one fraction that I flip, not 2 separate things. So I do have to do the adding first. So that's where it gets a little bit more complicated. So for here, 1 over a plus 1 over b. Now, there's nothing to factor. Your LCD is just going to be the 2 denominators combined, ab. And you're going to multiply by what's missing. So for the first fraction, you're going to multiply by b over b. And then for the other fraction, you're going to multiply by a over a. So here I have 1 times b is b and 1 times a is a. So I have b plus a over ab. And the order doesn't matter here for addition or multiplication, so you can rewrite it in the other order if you prefer. Then I would do the other one. So I'm going to come down here and do the same thing. My LCD is going to just be a cubed b cubed, because again, there's nothing to really factor there, so I'm just going to try to combine them. And you're going to multiply by what's missing. So it's going to be b cubed over b cubed. And then a cubed over a cubed. And then I'm left with basically the same idea, but everything is cubed. So you have a b cubed here plus an a cubed. Again, I'm just going to reverse the order because I like to have things in alphabetical order. If it's addition, it does not matter. Remember, addition and multiplication are commutative, so you can reverse that order. So now your problem becomes a plus b over ab divided by a cubed plus b cubed over a cubed b cubed. Now we can go ahead, change that to multiplication, and then you can go ahead and flip that fraction here. So a cubed b cubed over a cubed plus b cubed. Now you would try to factor, right? So a plus b I can't do anything with. The ab and the a cubed b cubed you can't break down, but I actually can break this down. So if you're not familiar, this is called the sum of cubes. And again, this is a factoring technique. There are formulas for the sum or the difference of cubes, so right here. And for sum of cubes, the formula is this. So a cubed plus b cubed is a plus b times a squared minus ab plus b squared. And that breakdown will always work. If you have different letters, let's say you have x and y, you would just substitute in. Or, if your b value was a 2, maybe this was like a cubed plus 8, so the b value is a 2 there. Again, you would just substitute that in. So this is the formula. So what this is going to look like then is going to be a plus b over ab times a cubed b cubed over a plus b a squared minus ab plus b squared. And again, we can now start canceling. So I can get rid of that a plus b. Now the nice thing about this formula here is you cannot break it down any further. So you don't have to try factoring this anymore. I can do a little work here though. So I have an a and an a cubed. I can cancel out one a. That would be a squared up here. And I have a b and a b cubed. So I can cancel out one b and I would have b squared. So my final answer here then, I have a squared and b squared left in the numerator. And then in the denominator, I have a squared minus ab plus b squared. So again, this one is pretty tough for multiple reasons. The big reason being that you have addition or subtraction. So that has to get cleaned up first if you're using this strategy. And this one was also tough because of the factoring. This is a formula that you may not have seen in a while. So this is a nice factoring formula to keep in mind. Now, the second strategy, which tends to be faster for the more complicated ones, I think, is to try to kind of cancel out this double fraction at the beginning. So what you do is you multiply everything by the LCD of all denominators at once. So instead of focusing on the numerator and denominator separately here, like the top and the bottom, you look at all denominators. So in this case here, right, my denominators are a, b, a cubed, and b cubed. So the LCD there is going to be a cubed, b cubed, right? Because I need both of those guys, but I don't need extra a's and b's. Those are already included. So I'm going to multiply my original by that LCD. I'll show you what that looks like. Okay, but don't forget that there really are parentheses here, so you do actually need to kind of distribute through to all parts. So I'm just going to take a little bit of time and write this out. So you'd have 1 over a times a cubed b cubed, and then you'd have 1 over b again, times a cubed b cubed. And the denominator, you have 1 over a cubed times a cubed b cubed, and 1 over b cubed times a cubed b cubed. So what I have here in the top, I can cancel 1a. So again, this becomes a square. I can cancel 1b. That becomes a square. In the denominator, I can cancel out the whole a cubed here and then the whole b cubed. And what I have left over, I have an a squared and a b cubed. I have a cubed and a b squared. And on the bottom, I have a b cubed plus an a cubed. And I can do a little bit more breaking down here. So notice that in the top, I can factor this. Both parts have at least a squared and b squared. So if I factor that out, from the first part, I would just have a b left. And from the second part, I would have an a left. And again, I can also rewrite this if you want to. So we don't have to use it kind of backwards. Addition is commutative, so I can switch the order here. Now, again, you have that same factoring piece, right? So I can go ahead and rewrite that denominator. So I have a squared, b squared, a plus b. That sum of cubes factors as a plus b, a squared minus ab plus b squared. You have that same a plus b canceling. And then finally, you have the same answer that we did before. So it's just a different strategy. Again, this one is a really tough problem. For me, if I have something simpler where there is no addition or subtraction, then I like to kind of just use this method. It's pretty fast, I think, to flip, see if there's anything in common that you can cancel and move on. When things get a little bit more complicated, students do tend to like this one because they can kind of clear it up a little bit faster, and you don't have to worry as much about the adding and subtracting with common denominators. But they're both good strategies, and they're both going to work. You just have to have a little bit more cleanup when you have addition and subtraction as well as that complex fraction. All right, so we're going to change gears a little bit now and start talking about radicals. Radical just means roots. So here, when there's no little symbol, it's just a radical sign, it's always a square root. When we have a different kind of root, we do put that little symbol in. So this is a cubed root. This would be an nth root and so on. That symbol is called an index if you see it there. And what happens here is it's basically the opposite of an exponent. So for instance, for the square root of 36, again, if there's no index, it's like having a 2. We don't write the 2 in because we do use it so often. But you'd ask yourself, well, what number squared, again, squared because of the 2 here, equals 36? Well, the number that squared equals 36 is going to be 6. When we do square roots, we don't use the negative version. So I know negative 6 squared is also 36. We don't do that unless the negative is on the outside, like this one here. Square root of 36 we just saw is 6. So now the answer is negative 6. When you're finding a square root, you consider it to be the positive version unless they tell you to find the negative. We call that the principal square root. Okay? So for instance, just to kind of do one more, square root of 25 is going to be 5 because, well, what number squared is 25? 5 is, right? 5 squared is 25. So you're going the opposite of an exponent. Here you have a 5. So you're asking yourself, okay, well, what number to the 5th power is 32 over 243? That's a tough one, but 2 to the 5th power is 32, and 3 to the 5th power is 243. So the answer here would be 2/3, right? 2 gets us the top, and 3 gets us the bottom. Now, when you're testing these out, powers blow up very, very quickly. So even though 243 seems large, only the number 3 was needed here, right? 3 to the 5th power was 3 times 3 times 3 times 3 times 3. It blows up very quickly. So if you're trying to guess and you're doing it by hand, start low. Here I have a cube. So I'm asking myself, okay, what number to the 3rd power would be -8? And the one that works there is -2. right? Negative 2 to the third power is negative 2, negative 2, negative 2. And this becomes positive 4, and then positive 4 times negative 2 is negative 8. So the answer here is negative 2. Now, this one's a little bit different. You have that negative on the inside. N to the fourth power equals negative 16. But you're going to see that nothing actually is going to work. If you try doing negative 2 again, you end up with positive 16, right? Because all your negatives are going to cancel. And it just doesn't work. So there is no solution here. It's not a real number. So there's no real solution. In a case like this, we do have imaginary numbers, but we're not going to talk about that just today. Or just yet, I should say. So a negative inside a even root. By even root, I mean a square root, a fourth root, a sixth root, etc., is not real. And that's because your negatives will always cancel out in pairs. So there's no way to get a negative number on the inside with an even root and have it be a real answer. Odd roots are fine. Negatives on the outside are fine. So it's only if the negative's on the inside and you have an even power, you're not going to get a real answer. You actually get an imaginary answer there, which again, we will talk about. All right, there are a lot of different rules here as well that we can use to help work with these radicals. So these are the properties of radicals. And these are ones where roots exist, right? So again, we're going to stick with non-imaginary numbers today, but real answers. So the first one basically, or the first two basically say that, the type of root and the power really cancel each other out. The only thing is if your power is even, the answer is always the absolute value of the inside. So for instance here, right, a square root, this would have a 2 as the index for the root, and you have a 2 for the power. So again, they basically cancel out, but you would just take the absolute value of the number, which is going to be positive 5. If you forget that, it's pretty easy to see, because if you do negative 5 squared, you do get 25. So that's where the answer really comes from. That's why you have the positive answer here and not the negatives, because when you square, that negative is going to go away. Here, again, those 3's basically cancel and you have negative 5. When it's an odd number, it's just whatever you see there. But again, if you forget, you can multiply this out. Negative 5 cubed is negative 125, and then the cube root of that really is negative 5. So if you forget some of these rules, you can always simplify first and then find the answer that way. For the next rule here, we're looking at 3, which basically says if you have the same kind of root, you can multiply underneath. So see how these both are roots 4. Then what I can do is I can take the fourth root and just do 4 times 5, which is 20. Now you would see if you could simplify further, but there is no number to the fourth power that's going to give you 20. So this is as good as this one is going to get. And it also works that way for division. So for division, you can go back and forth. You can separate them out, or you can bring them back together. So I'm going to skip to F for a second. So see how you have the same kind of root and it's being divided. You could also write this as the root of 72 over 6. And then 72 over 6 is 12. So you're able to simplify that a little bit more. Now, something else I want to show you, and this actually goes back to this third step here, is about breaking down multiplication, is we do like to simplify roots when we can. Now, I know I can't do the square root of 12. But if I think about 12 and I think about its factors, it's 1 times 12, 2 times 6, and then 3 times 4, I notice that I do have a factor that is a perfect square, right? Looking at here. So what I can do is I can break this down. 12 is the same thing as 4 times 3. And then the square root of 4 is 2. So we do use that rule, these rules going in both directions, where sometimes we'll put things back together, other times we'll break things back apart. But we do want to simplify radicals as much as we can. And it's going to be the same thing for e. I have root 50. I don't have an answer for that. But if I break down the 50, I have 1 times 50, 2 times 25, and 5 times 10. And I have a square root here, and notice that 25 would work with the square root. So I can break this down. 50 is 25 times 2. Square root of 25 is 5. So you do want to break these down as much as you can. If you have more than one option, so if you have multiple squares that work, then just choose the biggest one. D looks at step 5 here, which basically says that you can either do the exponent first or you can do the root first. It kind of doesn't matter. You can go back and forth. 8 to the 5th power is very large. So what I could do is take the cubed root of 8 first instead, and then do the 5th power. The cubed root of 8 is 2, because 2 to the 3rd power is 8. And then I do 2 to the 5th power, which is 32. So again, you can kind of go back and forth. Roots and powers are equal weighting, so you can do whichever one first. Now, the last 3 are a little bit trickier, but they use the rules that are above. So this one's another simplifying one, but what happens here doesn't simplify super nicely. So we're just going to break it down and take it all step by step. So I do have a square root here, so I'm going to think about that 216. And I can't do square root of 216, so I'm going to think about different factors. And you can use your calculator here to kind of divide 216 and see what works. And I do have that 216 is 36 times 6. And 36 definitely works here. Now, when I have a root as well, and I have variables that have powers, I want to think about the type of root it is. So here, it's a square root. So when I have variable exponents, I want my exponents to be divisible by whatever the index is. So here it's 2. So in this case, for our variables, we really want the exponent to divide by 2 here, whatever number is there. So the 4 is good, but the 5 is not. So what I could do is actually break this down. X to the 5th I could write as x to the 4th times x. Right? I still have 5 of them, but now I've broken it down where at least I can use that 4. So what I like to do here is I like to kind of split into the good stuff and the bad stuff, because this is pretty complicated. So I'm going to make one root that has the good stuff, the 36, the x to the 4th, and the y to the 4th. Those are all things that are going to simplify nicely. And then I'm going to use the other root for the leftovers. I have a 6 and I have an x that are not going to break down. Square root of 36 is 6. Square root of x to the 4th is x squared, and y to the 4th is y squared. So what happens there is you just take those exponents and divide it by the 2. That's how you get your new answer. And then I can't do anything with the second group. So when we have radicals like this, you're going to break them down as much as you can, and then anything that's left over that cannot be broken down will stay under the radical. When adding and subtracting with radicals, it's very similar to variables, right? If I were to add or subtract like 2x plus 5x, we could combine those together because they're the same type of thing. Well, I do need the same kind of root as well to add or subtract, but I can do some simplifying first. So 50 is 25 times 2, and 8 is 4 times 2, and I have square roots here, and 25 and 4 both work with square roots. So I'm going to break these down first. This 8 is going to stay on the outside, and then I would have the square root of 25 times the square root of 2 minus, again, that 3 is going to stay on the outside, and then this becomes square root of 4 times the square root of 2. Square root of 25 is 5. Square root of 4 is 2. And then I multiply whatever's left over. When working with roots, things that are on the outside multiply together, things that are under the root multiply together, right? Like up here, we multiplied under the root because they were the same kind of root. Here, we're going to multiply the outside stuff. You don't put the 8 under the root. So I end up with 40 root 2 minus 6 root 2. Now they're the same kind of root. We call these like roots. So you just subtract. 40 minus 36 is 34. And you keep the root 2, just like you would with keeping an x. So I do need the same kind of root as well here to add and subtract. For this one, think about distributive property. So use that distributive property first. So I have 5 times 4 is 20. Then I have 5 times 3 root 2. I'm just going to write that part out. On the next one, I have a negative 4 times root 2. So just be careful that 4 is outside the root. And then in the last one, I have negative root 2 times 3 root 2. Here, again, outside numbers multiply. So that becomes 15 root 2 minus 4 root 2. Here, you want to be a little careful. These are both the same kind of root, so actually those multiply inside, right? Because they're both inside the root. So this becomes 3, and then 2 times 2 is 4. Root 4 is just 2. So I have 20 plus 15 root 2 minus 4 root 2 minus 6, and then I can combine like terms. 20 minus 6 is 14. And then here, these are both root 2's. So 15 minus 4 is 11. So plus 11 root 2. So when multiplying, remember outside things multiply and inside things multiply. So here I have 2 roots, so I can, 2 of the same kind of root, so I can multiply the underneaths together. Here I have outside things, so the outside things get multiplied. All right, one last thing with these roots, I guess 2, So one is rationalizing denominators. And just like how we're very particular about final answers, when we have fractions, we like them always simplified, right? We like them to be reduced in lowest terms. We don't like radicals in the denominator. They just don't look nice. They're not wrong. We just don't like them. So we'd like to get rid of them. So I'm going to show you some examples on how you can get rid of those radicals in the denominator. And that is called rationalizing. So that's all it means. To remove the radicals in the denominator, it just means to rationalize the denominator. So for something like this, I can break this first apart into the top and the bottom. And then what you do, if you only have a simple fraction like this, it's a square root, you always multiply by whatever the denominator is. And remember that when you have roots that are the same, you multiply on the inside, right? So 3 times 2 is 6, and then 2 times 2 is 4. And what happens is the denominator should totally clear out. So root 6 I can't do anything with, but root 4 is 2. So by using the same square root in the denominator, you do get that clearing out. When you have a different kind of root, it is more complicated. You don't just rewrite the same thing again. So for square roots, you just write it again because you only need 2 of something that's squared. For cubes, you need 3 of something. So if I think about that 9 is 3 times 3. And I want it to be a cube. So I would really like to have another 3 here to get this to cancel out. So you have to actually think a little bit ahead about what other factor do you need to get this to cancel. So here I need 3 of something. I'm missing one of them. So I'm going to multiply by what's missing. So I have 2 times the cubed root of 3 in the numerator. And in the denominator, remember, you can multiply the insides together if it's the same root. So 9 times 3 is 27. And what to the third power is 27? Well, 3 to the third power is 27. So that denominator is going to become just 3. This looks a little weird, but this is just being multiplied 2 times the cubed root of 3. And we can write it this way here. When you have something more complicated and you have a square root with a plus or minus sign, we use what's called the conjugate. So if you have like a plus root b, you would use a minus root b. Or if you have a minus root b, you would use a plus root b. So you change that sign in the middle. Otherwise, you're going to leave the rest of it the same. And that's the trick that you use to write kind of problem. You do want to multiply it out though. So in the top, I'm going to have 21 minus 7 root 5. And in the denominator, we're going to multiply out. I get 3 times 3 is 9, minus 3 root 5, plus 3 root 5, minus root 5 times root 5. So I have 21 minus 7 root 5. What happens here in the middle is those cancel, right? Negative 3 and positive 3 are 0, so those cancel. Here, 5 times 5 is 25, so this becomes the square root of 25, which is just 5. So I have 21 minus 7 root 5 all over 4. You can also write it like this, 21 over 4 minus 7 root 5 over 4. That's also fine. You would want to check for simplifying. When you simplify, you just want to make sure they simplify outside the root, not inside. So as a little example here, let's say my problem was 6 root 2 over 2. You don't simplify under the root like this when you don't have a root here. You go this way. So 6 divided by 2 is 3. So you just want to be careful there. Remember, outside numbers go together for multiplying. Under the root numbers go together. So you would just check anything on the outside that can be reduced. The final piece here, and this is actually really helpful, is that roots are basically just exponents that are fractions. It's just another way to write it. This is a definition. And you want to notice that the number on the bottom is basically the index of the root. So that denominator is that root, and the numerator just works as a regular exponent. If you have a negative, negatives do mean to flip, so that does put that value in the denominator instead. So here, that 1 is like your exponent, and that 6 is your index or your radical. So I can rewrite this as 6 root m to the first power. So again, the radical is 6 and the power is just 1. Now the first power is just m, so I can rewrite it like this. You can put that root first or second, it doesn't matter. So whatever way is easier for that problem, you would go ahead and do that. So for this one, again, the top is like your exponent and the bottom is like your root. So this is the 4th root of 7 to the 3rd power, or you can write it as the 4th root of 7 to the 3rd power. They're both correct, and again, sometimes one is easier than the other. Here you do have that negative exponent, which basically means to take the reciprocal or flip. So this becomes 1 over 8 to the 5/3. Once you flip, the exponent becomes positive. So we have 1 over the cubed root of 8 to the 5th. Or I can also write this as 1 over the cubed root of 8 to the 5th. Now in this particular case, this way is nicer because I know the cubed root of 8 is 2. We've seen this one already. So if you can simplify, you would want to. So this becomes 2 to the 5th or 1 over 32. Here I can't do the 4th root of 7, and 7 cubed is very big. It doesn't help me either. So I can't simplify, but sometimes you can. So you do want to check to see if you can simplify it any further. We can go back and forth. So here you're starting in a root and you want to be back to the exponential form instead. So remember, the root part is your denominator and then the exponent part is your numerator. So this is x to the 3 over 6. And you can go ahead and simplify that fraction. That's 1/2. So again, you can keep going back and forth and just switching between the two forms if you like. This is the exponential form. But if you wanted to convert back over to the radical form, you could do that as well. So this is the way, 1/2 is the way you just write a basic square root. When you're doing your homework, make sure you're really careful. Do they want the exponential form or do they want the radical form? All right, simplify and then write your, sorry guys, final answer in radical notation. So I'm going to, there we go. The mailman came, so the dog is going a little crazy. So I'm going to start by simplifying as much as I can here. And I'm going to actually use my exponent rules first. So remember, if you're multiplying two things, we actually add those exponents. So I'm going to do that first. I do have a little bit of work to do here. I can multiply these both by 2 to get common denominators. Oops. And then I have 5, 6 plus 4, 6 is 9, 6. I do want to simplify that. I can divide those both by 3, and I get 3/2. So my problem actually becomes x to the 3/2. Now that's almost done, except for they don't want our answer in exponential form. They want it in radical here. So I am going to convert this back over. Remember, the bottom one is your radical. So this is actually the second root of x cubed. I don't really need the 2 there, right? Just the square root of x cubed. Now, you actually can break this down a little bit more. This is similar to the example we did. Let's see if I can find it real quick. Right here, where we broke down that x. So here I have a square root. I would like to have my power divisible by 2, which I don't. But I can break this down. I can write this as x squared times x. So this becomes the square root of x squared times the square root of x. The square root of x squared is just x. They just cancel each other out. Technically, it's the absolute value of x, but we'll assume that our x's are all positive here. And we would write our final answer in this way. So again, you want to just be careful when you have a root and an exponent, they do cancel. For even powers, technically it is the absolute value there, but we can just assume that our x's are positive in this case. Now, a really helpful application of this idea is actually on using your calculator. So let's say like you're on your calculator and you would like to find the 4th root of 625, and you're like, I don't have that button on my calculator. What you can do is you can convert it to an exponent. So this is the same thing as 625 to the 1/4 power. And most calculators can handle that. You may have to put your exponent in parentheses for it to recognize that it is a 1/4, not just like to the 1st power and then the whole number is divided by 4. So you may need to do that, but you can do that on your calculator as well. So it's just really helpful. If you're getting stuck on your roots, try to do it like this on your calculator. And practice with a number that you know, right? So for instance, we all know that the square root of 25 is 5. Well, square root of 25, I could also write as 25 to the 1/2. So try it on your calculator. Make sure you get the answer of 5. And that's a nice little tip, because a lot of calculators don't do kind of weird roots, and that is very helpful. All right, a lot that we covered again today as usual, looking at some of those just-in-time sections. If you have questions, make sure you send me a message, and otherwise I'll see you guys later.